Hi. So today we're going to look at two big topics that we have to finish off our discussion on limits, although we're going to be using limits pretty much for the remainder of the course. First thing we're going to talk about today is continuity. How do we determine whether or not a function is continuous? And then the second thing that we're going to talk about is the intermediate value theorem. The intermediate value theorem is something that's relatively simple to understand. It makes perfect sense the way it works and why it works the way that it does. But we're going to formalize things a little bit and talk about how we can show whether or not a function satisfies the intermediate value theorem. So I've gone ahead and written up on the board here the two main topics that we're going to look for. The first one here up on the top is the definition of continuity. We're going to say that we've got a function f, and that function is going to be continuous at some point c on the graph if the following three things apply. And that's important because it means that if you want to show that a function is continuous, we have to show that all three of these things are true. The first thing we have to show is that the value of the function at c actually exists. So if I were to plug in whatever the c value is, say my c value is 2, I want to know if the function is continuous at 2. If I plug 2 into the function, do I get a value? If I don't, then this first condition is not satisfied and the function is not continuous. The second requirement is that the limit as x approaches c from the left of the function has to be equal to the limit as x approaches c from the right. In other words, the two-sided limit has to exist. Now, for those of you that are AP students, this is an important piece of this. If you're asked to show that something is continuous, make sure that you talk about those one-sided limits and show that they're equal to each other. Then you can say that the two-sided limit exists. The third requirement is that the value of the function has to be equal to whatever that value of the two-sided limit is. So in other words, the limit, keep in mind, the limit existing doesn't guarantee continuity. It tells me that I'm approaching the same thing from both sides. The value of the function being the same as that limit fills in that little hole, makes the function continuous. Of course, the common kind of layman's definition of continuity is, can you draw the graph without picking up your pencil? If you can, then you have a continuous function. Okay? So we're going to look at some examples of continuity in just a second, but I wanted to go ahead and talk a little bit about the intermediate value theorem as well. This is a formal definition for it. We'll kind of simplify things a little bit as we're talking about this. The definition says, if f is continuous on a closed interval ab, and if some value w is any number that's between f of a and f of b, so we're talking about the y value. So w is somewhere on the y-axis, and it's between f of a and f of b, then there is at least one number c that falls inside the interval from a to b. C is going to be an x value between a and b, where f of c is equal to w. Now that sounds confusing a little bit. It's actually really simple to apply. We'll take a look at some examples of this as we move through toward the end of the video as well. So let's start off by taking a quick look at some functions and see if we can determine whether or not they're continuous. And if they aren't, we're going to see if we can determine which one of those three conditions aren't satisfied for it. So the first one that we're going to look at, let's look at the function f of x equals 5 divided by x minus 6. And we're going to see if that's continuous at the point x equals 6. Okay, so the first thing that I want to check is, does this function exist? Can I plug in a value and plug in 6 into the function and actually get a result? And in this case, you can see pretty easily that if I plug 6 into this function, if I try and evaluate f of 6, I get 5 divided by 6 minus 6, which is 5 divided by 0, which is undefined. And so the value of f of 6 doesn't exist. The first condition for continuity does not apply, and so this is not a continuous function at x equals 6. Now let's talk a little bit further about this and see if we can figure out what type of discontinuity this is. Notice up here that this is not a function that we can algebraically simplify. So there's no way for me to look at this and say, okay, the limit does exist or doesn't exist. In this case, if we look at this very much like we did in the last video where we were looking around 6, we can actually see that, and if we evaluate this, we can see that this is going to go to infinity on one side and it's going to go to negative infinity on the other. But we're not going to be able to cancel out the problem area. That means that this is a non-removable discontinuity. I can't remove the problem area. And this one actually causes an asymptote. So this is what we call an infinite discontinuity. And that type of discontinuity is non-removable. We cannot remove the problem. Okay? So if you have some kind of function like this where the value of the function doesn't exist at the point that you're interested in, you can't remove that problem by simplifying the function, then this is a non-removable infinite discontinuity. Okay? We didn't satisfy condition 1. So let's look at something maybe a little bit more complicated. Let's say that we had a piecewise function, maybe something like f of x equals, let's do x squared minus 16 divided by x minus 4, as long as x is not equal to 4. And then let's say that that's equal to 6 if x is equal to 4. And we're going to see if this is a continuous function at x equals 4. We're going to be looking at the point x equals 4. So the first thing that we want to look at is we want to say, okay, is this function defined when x equals 4? Well, I go through, first thing I'm going to do is look over here and I see that this is the part of the function that I need to use when x equals 4. So I'm going to plug 4 in over here, and sure enough, f of 4 is equal to 6. So the first condition is satisfied. I'm okay with that. Okay? Now, the second thing that I need to look at is I need to determine if the limit from the left and the limit from the right are equal to each other. I'm going to look at this and say, does the two-sided limit exist? So I'm going to take this top function here, because this is the function to use around 4, which is what I want to do for a limit. I'm going to see if I can find the limit as x approaches 4 of x squared minus 16 divided by x minus 4. And I can simplify that a little bit using the same strategies that we used in previous videos and say, okay, that's x plus 4 times x minus 4 divided by x minus 4. And sure enough, those will cancel, leaving me with the limit as x tends to 4 of x plus 4, which is 4 plus 4, which is 8. So sure enough, the second condition is satisfied. The limit from the left and the limit from the right are both going to be equal to 2 because I was able to find the going to be equal to 8 because I was able to find the two-sided limit. So the last condition was that in order for this to exist, in order for this to be continuous, the value of the limit has to be equal to the value of the function. And in this case, the value of the limit was 8. The value of the function was 6. Those are not equal to each other, so the third condition did not apply. This function is discontinuous, and in this case, we have a hole. And actually, this is going to be a hole regardless of whether or not we have this piece of information right here. Because even if the function was completely undefined there, when I graph this thing, it's going to have a hole in the graph right at x equals 4. This is a removable discontinuity because I'm able to algebraically remove the problem area and make this look like a continuous function. It's not continuous because I do have to look at the original function, and it's got a problem at x equals 4. Okay? So if I can remove the problem area, then this is called a removable discontinuity, and it means we have a hole in the graph. It's a very big distinction between whether or not you can or cannot eliminate the problem area and whether or not you have a hole in the graph or whether or not you have an asymptote. Both of those are types of discontinuities, though. Let's look at one more type of discontinuity. Let's say that we have, again, let's do a piecewise function. Let's say that we've got f of x is going to be equal to 1 if x is greater than or equal to 3, and it's going to be equal to negative 1 if x is less than 3. Okay? Now, I'm going to look at this and I'm going to say, okay, and we're going to see if it's continuous at x equals 3. So I look, first of all, is the function defined when x equals 3? I look at my function here, and let's see, when x equals 3, I'm using the top function, and sure enough, it tells me that f of 3 is going to be equal to 1. So the first condition is satisfied. I'm able to say that the function exists at the point that I'm interested in. So the second thing that I have to look at is, does this function have a limit that's the same from the left and from the right-hand side? So let's look at the limit as x approaches 3 from the left. The limit as x approaches 3 from the left, let's see, that means I'm looking at values like 2.9, 2.99, just to the left of 3. Anything less than 3, I'm using the bottom function here. And so as long as I'm to the left of 3, I'm going to be getting closer and closer to, and actually be at, in this case, -1. So the value of the limit from the left is equal to -1. If I look at the limit as x approaches 3 from the right-hand side, now I'm looking at numbers like 3.1, 3.01, things like that. Those numbers are greater than 3, so I'm using the top function, and that tells me that I'm going to be equal to -1. And you can see pretty easily here that the limit from the left is not equal to the limit from the right. And so this is also a discontinuous function. It means that the function, we're moving along at -1, and then all of a sudden we jumped up to 1. And that's why we give this the name that we do. This is called a jump discontinuity. Okay, so 3 different types of discontinuities that we can run into. We've got the infinite discontinuity, where we have a vertical asymptote in the graph. We have a removable discontinuity, or a hole in the graph. And then the third one is the jump discontinuity, where the function actually jumps from one value directly to the other value. All 3 of those things are going to cause discontinuity. So let's take a look at one more here. Let's say that we have, let's do another piecewise function. Let's say that we have the function f of x is equal to x squared minus 25 divided by x minus 5, as long as x does not equal 5. And let's say that it's equal to 10 if x does equal 5. Okay, this looks very similar to the one that we did a couple of times ago, but let's see what happens with this one, just to be sure. Last one we had a hole in the graph. Let's see if this one does as well. So again, first thing I want to look at is, does the function exist at f of 5? That's my first condition, and sure enough, I look at my function, when x equals 5, I'm supposed to be using the bottom function, and that tells me that f of 5 is going to be 10. I get a value, the first condition is satisfied. Second condition is that I have to see if the limit from the left is equal to the limit from the right. So let's evaluate the limit here. I'm going to evaluate this directly to the two-sided limit, like what we were talking about a second ago. We'll take the limit as x approaches 5, and as long as x isn't equal to 5, we're using the top function. So I'm going to be looking at x squared minus 25 divided by x minus 5. This will simplify, giving me the limit as x approaches 5 of x plus 5 times x minus 5 over x minus 5. Just like last time, and just like all our previous examples, the x minus 5s will cancel, leaving me with the limit as x approaches 5 of x plus 5, which I can evaluate the limit now. That's 5 plus 5, which is 10. So the two-sided limit does exist, so the second condition is satisfied. Now we have to look at the third condition. The third condition said that the value of the function had to be the same as the value of the limit. Well, the value of the limit that I found was going to be 10. So the limit, the two-sided limit exists and its value is 10. The value of the function at 5 is also 10. So the third condition is satisfied. So it turns out that this one is a continuous function. Now, if you look at the graph of this thing, it's actually a vertical, or excuse me, not vertical line, but it's a linear function that goes through the point 0, 5. So if I were to graph that, and then at x equals 5, if you just look at the top part, you have a hole right here at x equals 10. But because this is a piecewise function, this says when x equals 5, go ahead and plug in 10. When I do that, I fill in that hole, and that's what makes this one continuous. The one that we had a second ago didn't fill in that hole, it filled in a spot above the linear function, and so we weren't able to keep the continuity going. So that's the difference between whether or not a function is continuous or discontinuous, an example of the three different types of discontinuities that you're going to run into. Just remember that those three things that you need to show are always going to be true. You have to show that the function exists at that point. You have to show that the limit from the left at that point is equal to the limit from the right at that point. And then you have to show that the value of the limit is the same as the value of the function. If you can satisfy all three of those conditions, then you have a continuous function. Okay? Let's take a second and go back and look now at the intermediate value theorem. Like I said, the definition of that seemed relatively complicated, kind of wordy. Basically, what it's saying though is if you've got a function, we'll just draw in a little function here. Let's say that we've got, actually let's go ahead and drop this down to the axis, down below the axis. Let's say that I've got a function, doesn't matter what's going on over here outside of the interval that I'm working with. I'm going to put some vertical asymptotes in here and everything just to have fun. Okay, so let's say that this does something like this. Okay, and let's say that here is A, and let's say that here is B. Okay, so it doesn't matter what's happening to the function outside of that interval. The intermediate value theorem doesn't care what's happening outside of the interval that we're working with. So I'm only interested in what happens between here and here. And the first question I have to ask is the function continuous in that interval? Well, in that interval, you can see that, sure enough, this function is continuous. I'm going to go ahead and extend that down like that so we can see it. Sure enough, this function is continuous over that interval. And let's mark our values here. F of A is going to be here. F of B is going to be here. And if you remember in our definition for the intermediate value theorem, what it said was if you let W be any point between A and B, so if I choose any value between A and B, it can be anywhere in here, then there has to be some C value between A and B that will be equal to that function value. So let's say, for example, that this is W. Because this is a continuous function, there is at least one point where between A and B where there is a C that will hit that W. That's basically all it means. If you think about this, let's say you're thinking about temperature when it comes to weather. If the temperature goes from 80 degrees to 60 degrees over the course of a day, then at some point the temperature was exactly 75.231 degrees because that's a continuous function and it went from 80 to 60, so there had to be some time between when it was 80 and when it was 60 where I passed 60 or whatever number that was that I threw out there. I had to pass every value between 80 and 60 along the way. This is actually really helpful to us because one of the things that we're going to look at is, let's say you have a table of data and you're told, first of all, that you have a continuous function, f. So we're going to say f is continuous. And we'll just get a real quick, just a few pieces of a table here. Let's say here's my x value, here's my f of x value, and we'll just throw in some values here. Let's say we're going from 1 to 3 to 7 to 9. And then my f of x values, maybe they go from 6 to -2 to -4 to 5. Okay? Now I know that since f is continuous and at x equals 1 I was at 6 and at x equals 3 I was at -2, that means somewhere between the x value of 1 and 3 I had to have crossed the x-axis. The f of x value has to be 0 at some point between 1 and 3 because I have a continuous function and I went from a positive value to a negative value. So I have to have crossed 0 at some point. I can say that again over here, somewhere between somewhere between 7 and 9. I went from a negative value to a positive value, that means that I had to have gone from through the x-axis. I had to have crossed 0 at some point along the way. That's basically what the intermediate value theorem is telling us. So, two main topics that we were looking at here. The first one was continuity. Second one was intermediate value theorem. Both of those are important. We're going to be using them quite a bit over the course of the year.